So here is one of the handouts that I have, which is pretty much going to highlight some of these notions that we're going to talk about today. And so obviously I have no knowledge of your background. Some of you perhaps may be exposed to this thing here. Some of you are very new. Okay, we welcome you both. Okay, we can deal with you both. So what is the neural network? Okay, like question one. I'm sure most of you would know, have heard of it, know briefly what it is. But in a highlight mode, I'll tell you that neural networks inspired by the connectivity of the brain, and eventually people abstracted whatever they perceived or believed that this is information that they believe the network of the brain is performing. So there are a lot of neuroscience modeling, but the abstraction that we're using is very simple models that translates to interconnected networks. And nowadays what it is, you just have signals. If you're looking at the neural network as a processing network, I'm going to use the processing network, and there's also the other thing, processing and actuation. So remember when I talked about reinforcement learning, I said reinforcement learning is some network that's going to interact with the environment. It's like a robot, right? A robot sees, observes, what have you, and then it takes an action, moves, with things of that sort. But also we have gadgets or modules that basically want to determine what's in a picture, okay? Wants to understand what this speech. So that's really estimation or processing or understanding. So these are two kind of models of using this network. So bottom line, it's interconnected network with neurons receiving information initially from the external world, input signals, okay? And then if you adopt the structure that we say, which is cascaded structure, which is the natural form right now, you have a cascade or nested structure, then you have input, we call, okay, all the inputs the input vector or array or tensor, we call it a layer. Let's say it's layer 0, and that is connected somehow locally or globally, okay, by some parameters to another group of units. We call them layer 1, and then this layer 1 will be connected to layer 2 and what have you. Just repeat that same modules over. So from the input space, from engineering viewpoint, we have, if the input is a vector or we put it in a vector, if it's an array, we can form a vector, right? Then this vector is going to have a matrix which represents connectivity to produce for me, transform it into another level, another layer, okay? And then we add nonlinearity, and that we say, okay, here's one layer of a network. So we have an input layer, and then we have a weight matrix. Okay, that's why we need the linear algebra. And the matrix times this input vector is going to give you another vector, let's call it whatever, x or y, right? And then you have some nonlinearity act on it, and then the opposite linearity would be the first hidden layer. It's a representation. If you take that particular block and repeat it many times, cascade it, you have a feed-forward neural network, okay? Okay? So it's very simple. And at every layer, so you have a matrix times a vector of input signal plus maybe a bias vector, just to give you some freedom or flexibility in estimating the transformation. So it really is a transformation. And this transformation is cascaded because you have repeat that transformation many times. That's the engineering model we have, which is abstracting a very complex dynamic system model from neuroscience. That's at the simplest level, and this is not the only representation. This is one model representation that's referred to as feed-forward neural network. Okay. Questions? So really an input multiply by a matrix plus the bias, and then you squash everything by nonlinearity. This is one module, and repeating, cascading that module many times, you get multi-layers. That's how you get multi-layers. And the word deep came out from the need of having deep layers. So the cascade is going to go very deep. Yes?
So each layer, does it tackle a different problem, so to speak, in these neural networks?
It's a representation, yeah. And we'll go through the details. So right now I'm just giving you an overview of how things are, just to know what particular flavor, where this thing is, what a neural network is, just a cascaded structure. Now if you have a recurrency, that means when you have from one to the next layer, you could have another connection that feeds back. So feedback is referred to as recurrent, and feedback basically have its own contribution in enriching the capability of this model. Okay? So that's in a nutshell. And this explanation is very generic right now to anybody, even if you've never heard of neural network. Okay? Any questions about this generic description? So what translates from the complexity of the brain and neuroscience is interconnectivity, scale, meaning you have many of those units, okay? And what's that translate to? That translate to having a engineering model that has so many parameters, okay, that if somehow you discover the right parameters for your problem, you can have this cascaded model represent any arbitrary function. So there's some other universal approximation theories and a lot of deep things that you'll find in many textbooks and what have you. Okay? So I'm going to take a diversion a little bit here. Just tell you, we will be using this in the syllabus. You see basic reference to 2 online textbooks. The first one is Neural Networks and DeepLearning.com. It's in your syllabus. Okay? And we'll see it here again in these slides. Okay? And the other one is Deep Learning Book I believe net or something like that, or org, either net or org. We'll find out. Okay. The second book maybe is more advanced than the first one. The first one is really elementary. It's like mostly undergraduate kind of thing. It starts from scratch. The second one collects for you some of the basic math, maybe that at least you initially need. And this book, it's in a hard form and in printed form, and also it's online. And these people, their message is, we would like to keep it online because we need to update this book every 3 months. And they are doing it. So if you look at these 2 websites, this is the book maybe when was printed, I think maybe, I don't know, maybe last spring. That's when it came out. So now all the updates, all the stuff, they have it on that website. Maybe I should jump quickly and go, if I have that, and I'll just go to where, I think I have it in the syllabus, but I don't have it here. So here it is. Just jumping quickly, references would be Neural Networks and DeepLearning.com, and the other reference is DeepLearningBook.org. Okay? You can also, if you like, you can purchase the book, but you don't have to because this is available online. And I have also the class notes, which complements these things, which may be having more compact and direct about particular comments. And I think I'm jumping right now. Let me just discuss this slide since we're on it. So to become an expert, you need to keep up with this material, okay? If you're only looking at the class because of a grade, this is maybe not the class for you, okay? You really have to learn the stuff, and there's a lot of scattered information, and you have to learn those things. It's not more work for you. It's just you need to basically keep a tab on those things. Okay. And then the computing codes, especially in Python, there are other things, but bottom line, this book starts from scratch, and it has a lot of insights, that has been useful for undergraduate students to acquire appreciation of what neural network can and cannot do and how it relates to artificial intelligence and all this other stuff. And it's an easy read, okay? Somebody was jokingly saying that this could be a bedtime reading, okay? It's very easy and it's just common sense. This one obviously requires maybe more work, and I'm not really, by the way, advocating these are the only sources, but this is good source because they're free. They're available. You don't have to buy the book. Okay. So the libraries that we're going to go through, you could also go to I'm sorry if I can find it. There's also deeplearning.net, and that's a collection that was done by students some years ago, I think from University of Montreal, and they were collecting and keeping things. What I like about that is really the location where you can look at the software. So you look at the software and they list all the available software, and you can link and go to that particular website. I'm not obviously endorsing that particular location for other information or what have you, but I think for the software it's a nice place where you can find at least current software. The third resource for finding software, you just search it. It's all available. It's everywhere. Okay? So I'm going to go back to where we were here. So the models are very simple, and of course they scale up in complexity as we go along. If you really want to understand neural networks, you go beyond linear algebra. You have to look at differential equations of dynamical systems. That's when you really get into the deep stuff. And particularly when you get reinforcement learning, you have to have something about optimization, understanding of optimization, stochastic systems, and what have you, becomes very deep and capable. So why needed? Why we are using neural network? Why we're not using, for example, traditional signal processing or other techniques? Okay. Well, the main thing is that we are going to be tackling real world problems. Okay. And this approach says, I'm not going to predetermine if I'm going to use some filtering or some processing. I'm not going to specify fully the structure of the filter. Okay? So it's not a hand-made or hand-controlled, basically, structure. And that's what people like in many real-world problems, in image recognition and vision and speech, these kind of languages where tractable models don't exist. And if you want to have a physics-based model, you're going to have trouble justifying the physical-based models. So with that in the background, you basically have a parameterized model, and you have a nice modular repeatable structure of some form. We call it neural network, and we have this cascade one form. And you have so many parameters, and you say, okay, you wanted to know the relation of how we infer information from an image. There's some function that we don't know. There's some structure we don't know yet. So if I have this rich structure with many parameters, well, the claim is that there exist some parameters where if I plug them in, that whole cascaded network becomes that ideal function that's going to solve that particular problem for me. So at least now you have the capacity of the model is so universal. If you find the right parameters, that nice modular structure can emulate any particular magic function that does the work for you. So I don't have to handcraft the filter and specify what filter I'm going to have, a low-pass filter or high-pass filter or this filter or what have you. Or go to the frequency domain and cut that frequency, because a priori, I don't know that function I'm looking for. So the idea is to have a general structure, right, with enough parameters, and if you have that, you say, universal approximation theories, which we have many, can tell me that this structure is rich enough, capable enough to approximate any arbitrary function that I'm looking for. So that's step one. Okay? The next step, you say, okay, now I have this platform. I have the parameters. I don't know the parameters that will do the job for me. So how am I going to get those parameters? So we're going to link to training and optimization, training, validation, and testing and optimization techniques. Okay? So to answer the second question, why we're needed, because in real world problems, there exists some solution function that will do the job for detection or classification, but we don't know that function a priori. And we cannot handcraft it. And when we did handcraft it, it didn't work. Okay? That's the bottom line. So we deal with real world problems, unknown function. You start with parameterized, rich architecture of some sort, and we settled on this particular form of architectures we call neural network, whatever, feed forward, convolutional, whatever. We settled on these structures, and we have the parameters. Okay? So that's how you go and construct this one, which is layered or block networks. And then you say, okay, the way I'm going to find these parameters is through, quote unquote, unsupervised learning, supervised learning, reinforcement learning. So what does that mean? Well, that means you're going to have a cost function, sometimes referred to as a loss function, okay, which basically a criterion for supervised learning. You say, if I minimize that cost, that error, maybe related to the error of something, then I know I'm going to close the parameter. Use that cost function, and if you minimize it, you want to generate the parameters you're looking for. So there's an optimization technique which generate adaptively these parameters. So really that brings us to one method that has been dominant optimization called gradient descent or stochastic gradient descent. We inserted the word stochastic here for a purpose. We should always think in terms of stochastic processing, because in deterministic you'll be maybe too biased in one direction, what have you. You have to think in terms of stochastic. When you do the training, when you have some data, what do? You have, this is the available data. We have this huge YouTube videos that we could use for training. We have this huge, basically, speeches for a certain language that we can use for language. We have this huge database for one language and another language, English, Chinese, French, what have you, right? So we have lots of data, and every day we're generating a huge amount of data. And with the cell phones, we have data. There's no lack of data. So the idea is to use this available data, whether it's online or already in some reservoir or available in some cloud for your training. And typically what you do, you extract from this data a portion, and we'll say about how one would do that, from this data, and you say, this data, I'm going to use it for evaluation of performance of my training. And you have a big chunk of the data, you're going to use this data, I'm going to use it for training. Okay? And you may also have another data that you use for testing. So you could have training, validation, and testing. It's subdivided this way. Often what people do, they select data randomly. So they come and randomly select some sample of the data. Often maybe, let's say, 1/3 of the data will be for validation or something like that. Okay, or maybe 2/3 training, and then 1/6 and 1/6, something like that. And the key thing is to select this randomly. Okay? So don't chunk like the first whatever. Just randomly select these samples, yes.
So you're saying we do this on every training attempt, basically?
Yeah.
So every training attempt or training data is different, or validation data is different, or testing data is different?
No, the training will be the same. The validation is the same. Okay? So this is just, you do it on the outset.
But
just partition into those 3 parts.
But wouldn't it help the network perform better if we have like data of like 1 million things, and off of that we make 3 chunks randomly, and every training cycle we choose different chunks?
Yeah, there are a lot of different techniques, and I think we'll delve into many different forms of how to make the training basically more robust. There are a lot of different tricks and techniques in making sure you're not, what's the word is, overfitting. You have a set of data, you don't want to too biased to that data. So for example, the reason you have a training and you have validation is that when you do the training, and I don't want to jump ahead and, into details right now, because we'll be walking through those things, okay? But the idea is, when you're training, you don't want to be what's called overfitting with the training data. That means you have a filter or a network or what have you that knows this training data so well, and in the process, discriminate against other data. In your own mind, you should always think ahead that I'm after the testing data. I'm after the data that I haven't seen yet, right? So the whole goal of neural network, and that's what makes neural network unique and different, is that it uses the training data and the validation data as basically practice, simulation, scenario, preparation of when you get deployed to the real world. So you don't want to overtrain. So if your performance of the training data is not 100%, that's okay. As long as when I train it on the training data and I observe the performance of the validation is comparable to the training in terms of performance. So we have a testing and accuracy or performance. We have a training accuracy, and then validation accuracy or testing accuracy, okay? So you want to make sure that these things are comparable. You don't want to overtrain on the data, because with the training methodology, if you limit the set of data and you permit me to just train forever, I can get 100% accuracy on the data. But then you lose out on what you're after, which is really the unseen live data or test data. Very good. Okay. So there are a lot of benchmark and stories, and you could Google and search the network and find all the success stories. In fact, the reason that these big companies adopted these methodologies, these tech, because they found some value in these things in their own applications. So in speech recognition, in image recognition, in video recognition, detection, classification. So there are a lot of benchmarking, you see those things. Moreover, I'm going to share with you a website here which is called Kaggle.com. And basically it was a website that was created by people who are into the data science and neural networks and other data science techniques, machine learning in general, and other techniques as well. Really generically data science, which is broader than neural network and what have you. And they started competitions. And the competition, basically, they were able to enlist companies that come and say, here we have a problem, we have lots of data, we want to see if your techniques could actually solve this problem in terms of detecting something, classifying something, or predicting something, okay? You can go to this website, see all these past competition, the present competition, and now this particular company was acquired by Google, I think maybe this year or last year, most likely this year, beginning of this year. And now it's under the umbrella of Google, but Google left it to be the same way. They like this competition thing, which really anybody with any knowledge in data science can actually log in, you can have an account, you can participate in competition, yes.
I have a question about that. So you're saying there's competitions going on, right?
Yeah. You look it up.
Yeah.
I'm just sending you there to look it up.
Yeah, I have a question right there.
Yeah.
So like people submit their submissions, right? So can we like look at the code for the winning submission? Is it like open source of that?
Yes. And I urge you to go there and do the walk, and you're going to see a lot of information beyond what I can tell you here. But I think you have the codes and what have you, people actually, they're so kind that they volunteer their code. They have their codes there available. It's voluntarily. So people volunteer and they put their thing because people want to know in their community that their stuff is appreciated, they're appreciated. There are a lot of in this community, there's a lot of help from all sources, okay? And another location which I'm sure some of you or most of you are familiar with, the GitHub, github.com. How many people are familiar with that? Okay? So that's obviously is a public place where if you have any codes, you want to share it with the community, you have it there, and you can access other people's things as long as you're careful in terms of giving credit to what credit is due and what have you. So also, by the way, MSU also have MSU GitLab, which basically could be private for MSU, and you could use it, and you have a lot of resources, which is similar to GitHub, except it doesn't force you to be public if you don't need to, if you're not ready yet. So GitHub and GitLab. Okay. So so the one view in the, if you look at what neural network can overview, what are they doing basically? So all this layer stuff, in a way, performs transformation on the input data. So you have an input data to a transformation, and people can say, okay, what I'm doing, this transformation is going to give it a representation, a new internal representation, okay? And you could also say that what it's doing is actually creating an internal state of this processing. All these are equivalent things, depending when you use this state. If you view the system as dynamic, but if it's a static mapping, it's not a state, it's just a representation, okay? So the word representation is often used frequently. That's what the internal, basically, hidden layers or internal blocks are doing. They transform the initial data, which could be an image, into a different space that in the final space, this data could be classified separately. It becomes what we refer to as separable. I'm just throwing terms right now, we'll be revisiting those terms. So if you look at images, and you cannot distinguish, if you look at the image and represent the image as just a vector, you have a n by n image, 10 by 10 image. You say I'm going to represent it as a vector, which is a 100-dimensional vector. And if you take the images of everybody here and you create that vector, you say, I'm going to distinguish between the faces of these people, okay? This data in natural coordinate representation, the physical coordinate, sometimes not very separable. You have things, maybe different classes, they're tied up as vector representations, very close to one another. So that's not, the physical world doesn't have what we refer to as linearly separable. It's very difficult to classify things because you have things classified in a way that's very difficult. And if you want a Mickey Mouse example, think of the so-called XOR or XNOR problem, okay? So this is the basic, just maybe we'll talk about it some other time, but the XOR basically, you look at two signals, right? And where the two signals are the same, this is one class. The output is, let's say, 1 or 0, depending on XOR or XNOR, right? And where they're different, the output is class 1, okay, for example. But when you plot them in the state space, X and X1 and X2, you'll find you cannot partition these two classes linearly. What does that mean? In that example, you cannot have a line that partitions this in two classes. You're going to require more than a line. So you cannot, in the higher dimensional space, you cannot have a hyperplane that partitions two classes. So it is nonlinearly separable. You can separate it, but you're going to create basically an island and separate regions to classify the two classes. And I'm sorry I cannot really draw it for you right now. I'll be visiting it and walking through it, but I'm just throwing the XOR or XNOR as a problem example right now, showing you what's not linearly separable. So that the intuition says what all these cascade layers are doing to the incoming signal, which is initially very complex separation, different classes are really close to one another and merged together, unfold them in a way and put them in a way that could be in some dimensional space that are linearly separable, easily separate. If you achieve this, then you have a single layer neural network can actually partition this linearly separate. So we know already that if you have a single layer neural network or so-called support vector machine or 2 layers or something like that, these so-called, now people refer to them as shallow networks or not deep networks, these can basically separate optimally linearly separable data. So the depth stuff, what it's doing is just taking deep, complex transformation. The outcome of that complex transformation is that you finally get a state space or representation space or coordinate space where the original data is organized in a nice linearly separable classes. And then one layer at the end could actually separate those classes in class 1, class 2, class 3, class becomes easy. And then, so if you have things that are visually, they look very similar to one another, but distinguishing, they have some traits differently. When you pass it through the network, those two in the physical world, they look very similar. They actually be going the separate classes nicely in the final layer. So that's why this complex cascade network is doing, is that eventually unravel everything and puts things in a nice way. And if you succeed in that, then one simple layer can actually do the right classification. You don't have any error. Okay? So how would one do, if you have supervised learning, the supervised learning basically puts a criterion at the end. Just says, I have a target, which could be class 1, class 2, and I have the output, and I can have a measure of an error of some sort, and I have square that becomes basically L2 norm or some other norm. And now I have a scalar quantity, which is a loss function, cost function. And if I have a criterion of minimizing that cost function, I can spit out the right corrected weights or parameters that will do that transformation. Okay? So that's for supervised learning. So you impose it at the end, and then you backpropagate that imposition on all the parameters later. Okay? Yes?
Does that mean that the data has to be pre-classified?
I'm sorry?
The data has to be pre-classified?
Yeah, this is for the training mode. Yes, absolutely. Yeah. So that in the training mode, we already have exactly. You have samples of training data. This guy, here's the label, what have you. You train it on that. So use the training data to basically help for the supervised mode. On top of that, these so-called, we refer to them as hidden layers, which is all these layers we're talking about. Anything that's not an output and input layer is referred to as hidden layer. Very simple. Which is really a layer that represents a coordinate system, representation in between. And there are other techniques where you say, I don't really just make the update for all these different parameters based on just the cost for the supervised. I could create other techniques, unsupervised by some other metrics, okay, to train these hidden layers. Okay? All this stuff that I'm talking about, I'm just throwing things in the general form right now just to pique your interest and know what to ask when we walk through these things at the time. Okay?